Hello, and welcome to the first lecture. Today we're going to talk about exponents and radicals. An exponential expression, like the one here, has two pieces. The base, which is what is raised to the power, and the exponent itself, which raises the base to a different power. The base, a, can be any value, as well as the exponent. That can be any value as well. Right? So we want to talk about a few properties of exponents, right? And if we have any numbers a and n, right, we say a to the nth is just the product of a n times, right? So 2 to the fourth would just be 2 times 2 times 2 times 2, which if we evaluate would just be 16. If we have a negative n, right, a to the negative n is just the reciprocal. So something like 5 to the negative first, just be 1/5. 2/3 to the negative first, right? That would just be the reciprocal again, 3/2. This property says that anything to the 0th power is 1. And here, anything to the first power is just going to be itself. So if we look at a few examples, right? 2 to the first, well, that's just going to be 2 because the property says anything raised to the first is itself. 4 to the negative first, right? A negative exponent means I just take the reciprocal and raise that to the first again. So 4 to the negative 1 is just going to be 1/4. Likewise, 2/5 to the negative first is just the reciprocal, so 5/2. Now I've taken the reciprocal, so it's just 5/2 to the first, which again is just 5/2. If I look to evaluate -3 to the 0th, I look and I say, well, anything to the 0th is 1. And so we get that simplified. And we contrast that with the last example. Now the negative on the outside here means the only thing that gets raised to the 0th is that 3. So in fact, we can think of this as -3 to the 0th. In essence, that's just -1. Now if we have two things like a and b with exponents m and n, then we have the following properties. If our bases are the same and we're multiplying, then we just add the exponents. Right? If we take a power, like a to the nth, and raise it again to the mth, we just get to multiply the exponents, a to the m times n. Likewise, we could take a to the m first, and then raise that to the n. This one says if we have two things being multiplied and raise them both to the mth, then we can just distribute that power, a to the m, a times b to the m. And we want to contrast that with the fact that if we have a sum in between, right, that plus or minus, that we cannot just distribute, right? In this case, and we'll talk about this in a later case, that we're actually going to have to FOIL. So we can only distribute when it's multiplication or division inside. This next case is exactly when it's division inside. A divided by b, all raised to the mth, we can distribute that power down. And the fifth exponent is kind of the division version of the first property that says if we have the bases the same, a and a, and we're dividing, all we have to do is subtract the exponents. So let's do some examples, right? 2 to the third times 2 to the fifth. Well, these bases are the same, so I can just add their exponents. 2 to the eighth. And if we figure out 2 to the eighth, that is going to be 1/28. If we look at x squared to the third, we see that we're taking x squared and raising it to the third. So by our properties, we can multiply the exponents, or get x to the sixth. If we look at our third example, we can see we're multiplying inside. So I can, in fact, distribute that exponent of 5 through the two of them. Get 2 to the fifth, which is 32, and keep that x to the fifth. The fourth example, which has y over 4 squared, is exactly like the example before. We have division inside of my parentheses, so I can distribute that exponent, and I get y squared over 16. The fifth example, we get to, we're dividing, the bases are the same of 3, so in essence I can take the exponents and subtract them and get 3 to the negative 4. And whenever we have a negative exponent, it's like saying the reciprocal to that positive power. 3 to the fourth is just 81. And just for completion, if I look at this last example, x minus 1 squared, like I said, if I want to simplify that, I have to FOIL it, right? I can't distribute it because of this minus on the inside. So I'll have to do first, outer, inner, last. And again, we'll cover factoring later, but this just goes to show that I cannot just distribute this power. One thing that's important to talk about when we deal with exponents and radicals is the fact of nth roots. That if a to the n can be written as a number b, then we say a is the nth root of b. Another way we can see that is a is the nth root of b. Typically, if n equals 2, we call this the square root. Right? And when we deal with roots, there are a few things we want to talk about. If n is even, right? If we have an even root, or if n is odd, or if that means we have an odd root, right? That would be like the square root, fourth root, or an odd root would be something like to the fifth or a third root. So I'm going to say if what we have inside the root is positive, and we're looking at an even root, then we say that the value is going to have 2 real roots. So for example, that would be like the square root of 4. Right? The square root of 4 is both 2 and negative 2, because 2 times 2 is 4, as well as negative 2 times negative 2 is also 4. If n is odd, however, then b only has 1 real root. That would be something like 8, the cubed root of 8. That's just 2, because 2 times 2 times 2, that is 8. Right? If b is equal to 0, then any root of 0 is just 0. So that's fairly simple. And if b is negative, then we look at these two. If n is even, like a square root of negative 4, technically we would say that is imaginary. Right? That it wouldn't exist. So if n is even, then b has no real roots. However, that changes if n is odd. Right? The cubed root of negative 27, that would be negative 3. And it all deals with the number of things being multiplied. Here, when I have an odd root, it's like saying what number multiplied 3 times gives me negative 27. And of course, if I have an odd number of things multiplied, I'm still going to get a negative. And it turns out that the cubed root of negative 27 will just be negative 3. Right? And so the two ways we can write that, right, is the conventional nth root of b, or what we'll come in contact with a lot is 1 over n, b to the 1 over n. Right? That's how we can think of the nth root. Now if we look at these properties that we had before, right, the addition, when we multiply exponents together, when we can distribute exponents, these two things, or when we subtract exponents, right, they are going to work for roots as well. Right? So 2 to the 1/2, actually let's just go to the examples, right? 2 to the 1/2 times 2 to the negative 1/2 I can use the property that says if my bases are the same, I'll add my exponents. So 1/2 plus -1/2 is 0. And like we said before, anything to the 0th power is 1. Here, we have 81 to the 3/4. Now this is a little bit more difficult. And what we're going to do is we're going to use the fact that we have a numerator and a denominator. Right? We have a 3/4. What that allows us to do is take the property a to the m over n and say I can write this as the nth root of a raised to the mth power. So I can think of this as the 4th root of 81 cubed. Right? The 4th root of 81 is going to be 3, and I'm just left to cube that and get 27. If I look at the third example, all I have on the inside is multiplication. And so when I have multiplication, that's when I can distribute my powers. So I can write that as x to the 1, or 8 to the 1/3, sorry, then x to the 6 to the 1/3. That'll give me 2 x squared, because I want to multiply these. Finally, y over 4 to the -1. And as we've said before, anytime I see a negative exponent, I want to take my reciprocal of the inside and evaluate the positive exponent. And anything to the first power is itself, so that answer is just going to be 4 over y. One of the last things we want to do is learn how to simplify rational expressions. And so what we want to do is say here that anything under the radical has to be as simple. So an example of that would be the square root of x cubed. Since the square root is smaller than 3, this must be able to be reduced. And when I think about that, I want to say, how can I decompose x cubed so I have a perfect square? Right? So x cubed can be broken up into x squared times x. Right? I can split up my square root, and then the square root of x squared will just be x, and I'm left with root x. Right? And we can look at some others, like no power has to contain a common factor, radicals can't appear in denominators, and fractions can't appear within the radical. So let's take a look at simplifying this first expression. Right? We can take a look at the numerator first. We want to try and split this up into its different pieces. Right? So I can distribute this square root here, square root of 4, square root of x cubed, square root of y to the 6th. I can do the same thing here. Square root of 3, square root of x. And so look, the square root of 2, the square root of 4 simplifies to 2. We worked on the square root of x cubed, right? I can think of that as x squared times x, and the square root of y squared, square root of y to the 6th. And the bottom can't simplify at all anymore. Right? I can look at this piece now and say, I can simplify that x squared right here. That's going to be the x on the outside, and then a square root of x left over. This piece, the square root of y to the 6th will just be y to the 3rd over the square root of 3, square root of x. Right? I see these can cancel, and now I'm left with this. And so one of the things I wanted to say was, or I wanted to see to simplify this, is I can't have a square root in the denominator. So one way to get rid of that square root of 3 is to multiply by another square root of 3. But whatever I multiply on the bottom, I must multiply on the top. Right? I can't just multiply whatever I want anytime. I have to multiply on the numerator and the denominator. So my final answer will be 2 root 3 xy cubed, right? That's what my numerator is, all over 3. Because the square root of 3 times the square root of 3 will just be 3. one idea that we want to talk about is something called the conjugate. And if we have any expression, a plus b, its conjugate is a minus b. So, for example, if I look at x minus or x plus 3, its conjugate would be x minus 3. The exact same expression with the middle sign changed. Right? Likewise, if I have an expression a minus b, its conjugate is a plus b. So if I have negative 2 plus, if I have something like negative x minus 4, its conjugate would be negative x plus 4. So why might we want to learn about conjugates? Well, one of the ways to simplify was not having square roots in our denominator. So if we have an expression like this, where it's a square root and then plus a 2, the way we get rid of that square root is by multiplying by the conjugate, the square root of x minus 2, right? Like we said, if we're going to multiply the denominator by something, we have to multiply the numerator by it as well. And so the question is, why do we multiply by the conjugate? Well, when we multiply, we're going to have to FOIL. I'll get x minus 4 plus 2 root x minus 2 root x. Right? That's for the numerator. X root x minus 2x minus 4 root x plus 8. And if I look at this expression, plus 2 root x minus 2 root x, I notice that the root x's will cancel. And my whole denominator will just simplify to x minus 4. And that's the power of the conjugate. Right? It will get rid of radicals. And I'm just left with my kind of messy numerator. Right? That's about all we can do with the numerator. So hopefully this helps, and I will see you all in class on Friday. Thank you.